Dear friends, welcome to yet another installment of Orbital Geek. In this video, we explore the mystery of the Great Attractor, a super heavy force that is attracting our galaxy and many others toward a destination that no one knows. We're going to discover exactly what this cosmic phenomenon is and what might happen when we finally get there, if we get there at all. But is it a good idea to encounter something so powerful that it can warp space-time itself? Watch the video until the end to find out. And if you haven't subscribed to the channel yet, do it now and turn on the bell to receive all the latest updates. In the 1970s, astronomers studying the remnant light from the beginning of the universe, called the cosmic microwave background radiation, found something incredible. Our galaxy, along with everything inside it, including you, is moving through the universe at an incredibly high speed, like 630 kilometers per hour. This number is hard to imagine, so I'll simplify it. Since you started watching this video, you've already moved more than 11,000 miles, and you thought you were kind of chill, didn't you? It was a great achievement to accurately measure the speed of our galaxy for the first time. But at the same time, this was also a bit terrifying because no one knew exactly why the Milky Way was moving so fast. A good part of this movement could be explained by the expansion of the universe, which causes all objects in space to move according to something called the Hubble flow. The other part was caused by the gravitational interaction between the Milky Way and our neighboring galaxies, like Andromeda. But something didn't add up. It seemed like we were moving at a speed and direction that couldn't be fully explained. It was as if something huge and distant was attracting our entire galaxy onto a different path. This was intriguing, to say the least, but there was more. We found that not only was the Milky Way being pulled by that mysterious invisible object, all the galaxies around us, nearly 100,000 of them in an area spanning over 500 million light-years, are being drawn in the same direction by that unknown thing. This wasn't just intriguing, it was truly terrifying. Astronomers gave that mysterious object the name the Great Attractor, but coming up with a cool name was the easy part. The hard part was finding out what the heck this Great Attractor actually was. In the universe, there is only one force capable of moving entire galaxies off their usual courses over hundreds of millions of light years: gravity. This force results from the mass of an object. The more mass it has, the stronger its gravitational pull. To achieve attracting 100,000 galaxies over such an enormous distance, the Great Attractor has to be truly gigantic. When I say gigantic, I'm talking about something unimaginable, colossal, defying the rules of the universe. The question is, what is this object? And more importantly, what will happen to us when it finally catches us? First, let's deal with what the Great Attractor is. Normally, we study distant objects in space by using our telescopes to get a good look at them. However, to add to the mystery, when astronomers tried to gaze towards the Great Attractor with their trusty telescopes, they soon realized that this wasn't going to work this time. Our galaxy, the Milky Way, is a spiral about 100,000 light-years in diameter, and its 100 billion or more stars are all concentrated in a plane around 1,000 light-years thick. Unfortunately, whoever built this place seems to have left a lot of junk lying around. When we try to look out into deep space through the plane of our galaxy, our vision is practically blocked by enormous clouds of interstellar dust and gas. This part of the night sky that gets obscured by the plane of the Milky Way is called the zone of avoidance, and it blocks our vision of about 10% of the universe. And guess what? The Great Attractor is smack dab in the middle of that. So, for several decades after the discovery of the Great Attractor, its true nature remained a complete mystery to us. We could only study the Great Attractor indirectly, by analyzing its gravitational impact on the surrounding galaxies. While this didn't give us many details, we managed to estimate its approximate location between 150 and 250 million light-years away, in the direction of the Norma constellation. For the first time, we got an idea of just how massive it is. According to our current estimates, the Great Attractor has a mass equivalent to 10 quadrillion suns. Back then, that number simply didn't make sense. Nothing we knew of in the universe came even close to that size. To this day, the single largest thing we found is an ultramassive black hole called TON 618, which is so mind-bogglingly huge that I sometimes think astronomers made it up as a joke. This black hole is nearly 250 billion miles across and powers a quasar with an output equivalent to 140 trillion suns. It may be the largest thing that has ever existed or will exist in our universe. It's a true hell of destruction, but still, its mass is estimated to be only 66 billion solar masses. Not too shabby for a black hole, but it's still about 150,000 times less massive than the Great Attractor. By the way, scientists may have found an even more massive, ultramassive black hole, Phoenix A, with around 100 billion solar masses, but there's an ongoing debate about its actual size. Regardless of the largest, the question remains: if the biggest thing in the known universe isn't massive enough to explain the gravitational effect of the Great Attractor, then what could it be? Normally, this is the part of the video where I'd say that, for now we have no idea, but this time, we really do. As I mentioned before, it's nearly impossible to study the Great Attractor directly using standard telescopes, which mostly detect visible light. However, we're not limited to just visible wavelengths, and in the last 40 years since the discovery of the Great Attractor, we've made great strides with radio and infrared telescopes. With these new technologies, we finally managed to peer beyond the zone of avoidance and sneak a quick look at the area of the sky where the mysterious and enormous Great Attractor is located. So, what did we find there? A gigantic black hole? An intergalactic megastructure built by super-advanced aliens? Kanye West's ego? Unfortunately not. What we found were more galaxies. Lots of galaxies. It may not sound very exciting, but seeing what lay beyond the zone of avoidance helped us understand the true nature of the Great Attractor. And it wasn't anything we were expecting. To explain what we found, we need to quickly rewind to the beginning of time. The universe isn't just a random mess of 2 trillion galaxies randomly tossed about space. It actually possesses a large-scale structure we call the cosmic web. We're still not exactly sure why this structure exists, but the most accepted theory is that the early universe wasn't uniform. There were variations in the distribution of matter. The denser regions had more mass, and therefore more gravity, which caused them to attract even more matter around them. Over billions of years, those dense regions became denser, while the less dense regions remained more empty. We can think of this as a kind of cosmic capitalism, where gravity gradually shaped the universe we know today, creating huge structures and leaving vast empty areas in between them. The structures we see in the universe follow a clear hierarchical order. To simplify a bit, stars come together to form galaxies, galaxies form groups and clusters, and these group together to form superclusters. In our neck of the universe, it looks like this. Our star is part of the Milky Way, which is one of about 40 galaxies in the local group. In turn, the local group is part of about 100 groups and clusters that make up the massive Virgo supercluster. For a long time, we thought the Virgo supercluster was the limit of our cosmic neighborhood, but we were wrong. When we finally managed to see beyond the zone of avoidance, we realized that the Virgo supercluster, with its about 45,000 galaxies, was just a part of a much larger structure, the Laniakea supercluster. At this point, we're so far up in scale that the numbers become almost meaningless for human comprehension. But just for the record, the Laniakea supercluster is about 520 million light-years across and harbors around 100,000 galaxies. In short, it's truly ginormous. But here's the crucial point. The mysterious Great Attractor isn't just located in the middle of it. It is the Laniakea supercluster itself. This is what we discovered when we finally managed to peer beyond the zone of avoidance. The Great Attractor isn't an object, it's a place. We often compare space-time to a trampoline. While this analogy has its limitations, it serves our purpose here. Imagine placing a heavy object in the middle of the trampoline. It will deform the surface, showing how space-time curves. The bigger the object, the more the deformation and the stronger the gravity. The Great Attractor is simply the deepest point in that trampoline in our corner of the universe, the gravitational center of a vast cosmic structure toward which all the surrounding galaxies are being drawn. We're reasonably sure we've discovered what the Great Attractor is, but as for what will happen to us when we get there, things get a bit more complex. The Great Attractor is about 200 million light-years away, to simplify. If we keep heading in its direction at our current speed of 630 kilometers per hour, we estimate we'll arrive there in about 95 billion years. However, we'll never actually reach the Great Attractor. The reason is that the universe is expanding, and this expansion is accelerating. Even though we're moving rapidly toward the center of the Laniakea supercluster, the distance to the Great Attractor will eventually start increasing, despite our velocity towards it. It can be confusing, so here's another example. Imagine two ants walking towards each other on the surface of a balloon. If the balloon maintains its size, the ants will eventually meet and greet each other. However, if you start inflating the balloon, the distance between them will increase. If you inflate the balloon fast enough, no matter how quickly the ants scurry, they'll keep getting farther apart. That's basically what will happen to the Milky Way and the Laniakea supercluster. So unfortunately, our descendants will never get to greet the Great Attractor. For those who enjoy pondering existentialism, it's important to note that the expansion of the universe won't just drive us away from the Laniakea supercluster, it will completely isolate us from everything else. The currently observable universe is about 93 billion light-years across and harbors around 2 trillion galaxies. Only about 40 of those galaxies, belonging to the local group, are gravitationally bound to us. They'll be our companions forever. However, due to the expansion of the universe, the rest of the galaxies will start receding into the cold, dark depths of space at a speed greater than light, at least relative to us. Since nothing in the universe can exceed the speed of light, no human being will ever be able to explore those galaxies, no matter how long our species survives or how advanced it becomes. Not even the starlight from those galaxies will be able to reach us. Thus, the great cosmic web we know today will vanish. The enigmatic nature of the Great Attractor is a fascinating challenge for modern science. We only know that this colossal concentration of mass, equivalent to 10 quadrillion suns, is warping the very fabric of space-time and drawing everything around it, including our galaxy, on an unprecedented cosmic journey. However, due to the accelerating expansion of the universe, we may never reach the Great Attractor. The big question that remains is, does the Great Attractor mark the beginning of a new cosmic cycle, or does it signal an intergalactic apocalypse from which there is no return? Leave your thoughts in the comments on this mystery that challenges our most basic notions about the universe we live in.